Beneath the starry skies we gaze upon lies a hidden reality, a universe where everything we see, from galaxies to planets, makes up less than 5% of the cosmic tapestry. The rest, a shadowy realm of dark matter and dark energy, invisible forces shaping the universe in ways we're only beginning to grasp. For decades, astronomers have pieced together clues like cosmic detectives, uncovering bizarre phenomena that defy explanation. Strange gravitational pulls, galaxies moving faster than they should, and an expansion of space that's speeding up when it should be slowing down. These aren't plot twists from a sci-fi novel, they're real mysteries written into the fabric of reality itself. What is dark matter? Why does dark energy seem to be tearing the universe apart? And could the answers rewrite the laws of physics as we know them? Strap in, we're about to explore the 30 most mind-bending puzzles of the dark universe, where every discovery leads to deeper questions and the thrilling possibility that we're on the verge of something revolutionary. Think of the universe as a colossal construction project where visible matter stars, planets, and galaxies are merely the finished buildings, but what holds them up? The hidden scaffolding, dark matter. This mysterious substance doesn't glow, cast shadows, or interact with light in any way, yet its gravitational grip is strong enough to keep entire galaxies from flying apart. Without it, the night sky as we know it wouldn't exist. Galaxies spin so fast, the math says they should tear themselves to pieces, unless there's something unseen adding extra gravity. That's the first major clue astronomers found. Dark matter isn't just floating around randomly. It forms vast, intricate webs stretching across the cosmos, guiding where galaxies form and how they move. It's the cosmic architect behind the grand design of the universe. But if we can't see it, how do we know it's real? The evidence is everywhere. Light bends around invisible concentrations of mass like a car swerving around a hidden obstacle. Entire clusters of galaxies move in ways that only make sense if there's far more matter than what's visible. Even the way the universe expanded after the Big Bear hints at dark matter's crucial role. So what is it? Leading theories suggest it could be a yet undiscovered particle, something entirely outside our current physics. Experiments deep underground and in giant colliders are searching for traces. Others propose even wilder ideas. Could dark matter be primordial black holes or a flicker from another dimension? Whatever the answer, cracking this mystery won't just fill in a blank in our cosmic map. It could rewrite the rules of reality itself. Just when astronomers thought they had a handle on the universe's expansion, nature threw another curveball. In the late 1990s, two teams studying distant supernova stumbled upon something that should have been impossible. The expansion of space wasn't slowing down as expected. It was accelerating, as if some unseen force was pressing harder on the cosmic gas pedal. This wasn't just strange, it defied everything physics predicted. The culprit, dark energy, a mysterious repulsive force woven into the very fabric of space. Unlike dark matter, which holds galaxies together with its gravitational pull, dark energy does the opposite. Imagine blowing up a balloon with tiny dots drawn on its surface. As the balloon inflates, the dots move apart. Now, picture the balloon inflating faster and faster with no extra air being added. That's what dark energy is doing to the universe, stretching galaxies away from each other at speeds that keep increasing. The numbers alone are staggering. Dark energy makes up roughly 68% of the universe's total energy content, dwarfing even dark matter, yet we know almost nothing about it. Is it an unchanging property of space itself, what Einstein once called the cosmological constant? Or could it be a dynamic force growing stronger or weaker over time? The answer could determine whether the universe continues expanding indefinitely, ripping apart galaxy clusters, stars, and even atoms in a far future event cosmologists ominously call the Big Rip. Efforts to solve this puzzle are in full swing. Telescopes like the Dark Energy Survey and the upcoming Euclid space mission map the large-scale structure of the cosmos, hunting for subtle clues in how galaxies cluster. Other researchers are probing whether our understanding of gravity itself needs an overhaul. One thing's certain: dark energy isn't just another cosmic mystery. It's the invisible hand shaping the ultimate fate of everything that exists. Picture one of the most violent events in the cosmos, a head-on collision between two massive galaxy clusters, each containing hundreds of galaxies. When these titanic structures slammed into each other, they didn't just leave chaos in their wake, they handed scientists a breakthrough. The bullet cluster, named for its bullet-like shape in X-ray images, became the smoking gun in the hunt for dark matter. Here's what made this cosmic wreck so revealing. The cluster's hot gas visible in X-rays collided and slowed down like two clouds of smoke merging. But something else kept racing ahead unimpeded, the vast majority of the mass invisible to telescopes. How do we know? Because background galaxies behind the clusters appeared distorted, their light bent by gravity in ways that mapped exactly where the unseen mass had to be. The verdict: dark matter had outrun the gas, proving it doesn't interact with normal matter the way everyday objects do. This wasn't just a lucky observation, it was a game changer. Skeptics had argued that maybe dark matter didn't exist at all, and that gravity just worked differently on cosmic scales. But the bullet cluster showed that the laws of physics do hold. We just hadn't accounted for an entire invisible component of the universe. The separation between visible gas and gravitational pull was too precise, too unmistakable to dismiss. Since then, other collision cluster discoveries have reinforced the case. Each one acts like a cosmic experiment, peeling back another layer of dark matter's secrets. Yet for all we've learned, the bullet cluster still raises new questions. Why doesn't dark matter interact with light or normal matter? Could it have its own hidden forces, its own cosmic rules? One thing's certain: this celestial crash site didn't just confirm dark matter's existence. It turned speculation into solid science, forcing us to confront just how much of the universe remains hidden in plain sight. Here's the next segment of the script, crafted to flow naturally from the previous discussion while diving into modified Newtonian dynamics, and with fresh engagement and clarity. For centuries, Newton's laws of gravity seemed unshakable until Einstein reimagined them. Now, another revolution might be brewing. What if the cosmos doesn't need dark matter at all? Enter modified Newtonian dynamics, or a daring idea that flips the script entirely. Instead of invoking unseen matter to explain galactic behavior, suggests we've been missing something far more fundamental. Gravity itself might play by different rules on cosmic scales. At the heart of is a simple but radical tweak. When the gravitational pull between objects becomes incredibly weak, like at the fringes of galaxies, the force doesn't fade as quickly as Newton or Einstein predicted. This tiny adjustment neatly explains why stars in spiral galaxies orbit at speeds that should fling them into space. No dark matter required. For some galaxies, predictions match observations better than the dark matter model, like a key fitting a lock everyone assumed was broken. But the universe loves throwing wrenches into elegant theories. While excels with individual galaxies, it stumbles when faced with cosmic heavyweights like the bullet cluster. Remember how dark matter's gravitational fingerprint separated from visible matter during that collision. Struggles to replicate that smoking gun evidence without adding hidden mass back into the equation. Critics argue it's a patchwork fix, adjusting gravity here, quietly borrowing dark matter there. Yet the theory refuses to fade. Its proponents, a vocal minority of physicists, see it as a rallying cry to question dogma. Could Einstein's relativity, however brilliant, be incomplete? After all, history shows science advances when anomalies force us to rethink the rules. Mund persistence keeps the debate alive, pushing both sides to sharpen their arguments. Telescopes now hunt for ultra-diffuse galaxy systems so faint they're perfect labs to test Mund limits. Meanwhile, dark matter experiments grow ever more sensitive, racing to detect particles that might not exist. The stakes couldn't be higher. If Mund is right, we're on the verge of rewriting cosmology's foundation. If it's wrong, its very existence reminds us how much we still don't understand about the dark universe. One thing's clear: in this tug-of-war between invisible matter and tweaked gravity, the cosmos always has the final word. This segment maintains the script's momentum while introducing Mund with accessible analogies, acknowledging its strengths and weaknesses, and framing it as a provocative challenge to mainstream cosmology. The tone remains authoritative yet conversational, inviting viewers to ponder big questions without overwhelming them. Let me know if you'd like any refinements. Hidden in the chaotic moments after the Big Bang, when the universe was hotter than the core of a star, something bizarre may have emerged: black holes unlike any we've seen before. Not born from collapsing stars, but forged in the intense pressure and density of creation's first seconds. These are primordial black holes, and they might be the universe's oldest trick. Unlike their stellar counterparts, these objects could be almost any size, from smaller than an atom to larger than a planet. The lighter ones may have already evaporated thanks to Hawking radiation. But the middleweight suspects, those with the mass of a mountain packed into the width of a proton, could still be out there, drifting unseen through galaxies. And here's the kicker: if enough of them exist, they'd exert the exact gravitational pull we attribute to dark matter. Gravitational wave observatories like LIGO have given this idea new life. Some of the black hole mergers they've detected seem oddly heavy, raising eyebrows among theorists. Could these be primordial black holes, relics from the universe's first moments? Others look for subtle distortions in starlight, a telltale flicker if one of these invisible objects passes between Earth and a distant star, yet hurdles remain. If primordial black holes were common enough to account for all dark matter, we'd expect to see more gravitational lensing effects than we do. Some models suggest they'd have disrupted the delicate process of galaxy formation. Still, the possibility lingers: an elegant solution hiding in plain sight. After all, what better place for dark matter to lurk than inside black holes so ancient they predate the first stars? If we ever find them, it wouldn't just solve one cosmic mystery. It'd rewrite the story of how everything began. Deep beneath mountains and abandoned mine shafts, scientists have built some of the quietest places on Earth, not to escape the world, but to listen for whispers from the cosmos. These ultra-sensitive laboratories, shielded by rock from cosmic interference, are hunting for ghostly particles that could be the very essence of dark matter, WIMP, or weakly interacting massive particles. The theory behind WIMP is both simple and elegant. If dark matter makes up most of the universe's mass, it must consist of particles that don't absorb, reflect, or emit light yet still exert gravity. WIMP fit the bill perfectly, interacting only through gravity and the weak nuclear force which governs radioactive decay. Billions could be streaming through your body right now, leaving no trace. For decades, physicists have bet big on WIMP, designing intricate detectors filled with liquid xenon or supercooled germanium crystals. The idea: if a WIMP occasionally bumps into an atomic nucleus, the faint recoil might be captured, a cosmic ping in an otherwise silent void. Yet despite heroic efforts from Italy's Gran Sasso Lab to South Dakota's Sanford Underground Research Facility, no definitive signal has emerged. Could we be chasing shadows? Some researchers argue WIMP might be lighter or heavier than predicted, or interact even more weakly than imagined. others suggest we may need entirely new detection methods, like hunting for the ripples WIMP leave as they pass through Earth's magnetic field. The lack of evidence hasn't killed the theory, though. In fact, it sparked more creative experiments like repurposing ancient minerals as fossilized WIMP detectors. What makes this hunt so thrilling is the sheer scale of possibilities. If WIMP exist, they could bridge gaps in particle physics, answering why the universe has more matter than antimatter. Or they might hint at entirely new dimensions, but if they don't, well, that's just as revolutionary, a sign that dark matter is even stranger than we dared to guess. Either way, the silence underground isn't failure, it's the sound of science pushing deeper into the unknown. The universe loves its symmetry, but sometimes nature throws in a subtle twist. Enter Axions, hypothetical particles so lightweight they blur the line between matter and ripple. Born from an elegant solution to one of quantum physics' nagging problems, these cosmic phantoms might be hiding in plain sight as the very fabric of dark matter. Here's where the plot thickens. In the 1970s, physicists noticed something odd about neutrons, the neutral particles in atomic nuclei. When placed in strong magnetic fields, they refused to wobble as much as theory predicted. This tiny discrepancy, called the strong CP problem, hinted at a missing piece in our understanding of quantum forces. The proposed fix, Axions particles that essentially act as nature's symmetry enforcers, quietly correcting the math of the subatomic world. But Axions didn't stop there. Researchers soon realized these elusive particles could pull double duty. If they exist in vast enough numbers, their collective gravity might explain dark matter's invisible pull. Unlike WIMP, Axions would be staggeringly light, potentially billions of times less massive than an electron, but their sheer abundance could fill the cosmic ledger. Picture a swarm of fireflies so dense their combined glow outshines the sun. Now replace light with gravity, and you've got the Axion dark matter hypothesis. Hunting them requires equal parts ingenuity and patience. Since Axions might convert into faint microwave photons in magnetic fields, experiments like ADMCs, the Axion dark matter experiment operate like cosmic radio receivers. Hidden in a vault at the University of Washington, ADMC's supercooled cavity tunes through frequencies, searching for the telltale hum of Axions turning into light. It's less a particle collision and more like listening for a whisper in a hurricane. The implications of a discovery would ripple far beyond dark matter. Axions could unlock secrets about the early universe's conditions, explain why matter dominates antimatter, or even hint at extra dimensions. Critics point out that despite decades of searching, no Axion signal has been confirmed. Yet the search grows hotter, with new projects like Europe's MADMAX and South Korea's Koltask joining the hunt. Whether Axions exist or not, their story embodies science at its most daring, turning a tiny anomaly in neutron behavior into a candidate for the universe's greatest mystery. Sometimes the smallest ideas cast the longest shadows. Imagine if the forces governing dark matter operated like an entirely separate universe, one with its own rules, its own energy, and even its own version of light. That's the tantalizing promise of dark photons, hypothetical particles that could act as messengers between ordinary matter and the shadowy realm of dark matter. If they exist, they'd represent a bridge between our familiar world and a hidden cosmic layer we've barely begun to glimpse. Unlike the photons we know, particles of light that make up everything from sunshine to radio waves, dark photons wouldn't interact with our electromagnetic forces. Instead, they might ferry energy and momentum exclusively within dark matter's invisible domain. Think of it like this. If ordinary photons are the postal service of our universe, dark photons could be the encrypted couriers of a secret parallel society. The hunt for these elusive particles is heating up in laboratories worldwide. particle colliders like CERN Large Hadron Collider are smashing atoms at unprecedented energies, searching for fleeting signs of dark photons decaying into detectable particles. Underground experiments shielded from cosmic noise monitor sensitive detectors for unexpected energy spikes, potential signals of a dark photon's brief appearance. Even astrophysical observations play a role. If dark photons mediate forces between dark matter particles, their effects might subtly alter how galaxies move or how cosmic rays travel through space. But why does this matter beyond solving an abstract puzzle? Because dark photons could be the first clue to a dark sector, a whole family of undiscovered particles and forces operating invisibly alongside our own. Some theories suggest dark photons might occasionally mix with ordinary photons, creating rare but detectable interactions. Others propose they could decay into known particles, leaving behind faint but recognizable fingerprints in high-energy collisions. Skeptics argue that without direct evidence, dark photons remain speculative, yet their existence would elegantly address multiple mysteries at once, from why dark matter seems so aloof to whether undiscovered forces shape the cosmos in ways we've yet to imagine. Every null result in the search isn't a dead end. It's a narrowing of possibilities, inching us closer to answers. Whether dark photons are real or not, their theoretical allure highlights just how much we still have to learn. The universe may not play by the rules we've written, and that's what makes the hunt so exhilarating. If we find them, it won't just be a new particle. It'll be a doorway to a hidden dimension of reality waiting to be explored. Astronomers have a problem, and it's not just a small margin of error. It's a full-blown cosmic contradiction that's shaking the foundations of modern cosmology. Meet the Hubble tension, a stubborn mismatch in two of the most trusted ways we measure the universe's expansion. On one side, we have precision observations of the early universe, like the cosmic microwave background. On the other, measurements of nearby galaxies and supernova. Both methods are meticulous, both backed by decades of research. Yet they disagree by a jaw-dropping 10% on how fast space is stretching. That's not just a rounding error, it's a gap wide enough to suggest something fundamental is missing from our textbooks. So why does this matter? Think of it like building a bridge where the two halves don't line up. Either someone misread the blueprints or there's a hidden force warping the structure. In cosmology terms, the blueprints are our standard model Lambda CDM, which has beautifully explained everything from galaxy formation to the Big Bang's afterglow. But the Hubble tension is its first major crack. Some theorists argue it could mean dark energy isn't constant but evolving, growing stronger over time. Others wonder if exotic particles or even undiscovered dimensions are tweaking the cosmic math. Then there's the unsettling third option: maybe our tools are flawed. After all, measuring the universe's expansion is like trying to gauge the speed of a train while standing on its roof. Distant supernovae act as mile markers, their brightness revealing how fast space stretches between us and them. Nearby Cepheid variable stars, cosmic lighthouses with predictable pulses, help calibrate the scale. But tiny errors in these measurements could snowball into the disparity we see. The stakes couldn't be higher. If the tension stems from new physics, we're on the verge of rewriting cosmology's rulebook. If it's observational, it means rechecking every assumption in our cosmic playbook, from how starlight dims through dust to whether supernovae behave differently across cosmic time. Projects like the James Webb Space Telescope are now double-checking distances to Cepheids, while next-generation observatories like the Vera Rubin Telescope will map millions of galaxies for fresh clues. One thing's certain: the Hubble tension isn't just a technical hiccup. It's a beacon pointing to the next frontier in our understanding of the cosmos, whether that frontier hides unknown forces, invisible flaws in our methods, or something nobody's even dreamed up yet. And that's what makes this crisis so thrilling. In science, contradictions aren't dead ends. They're invitations to dig deeper. Gaze into the deepest maps of the cosmos and you'll see it, a sprawling, intricate network of galaxies stretching across billions of light years like luminescent threads in a tapestry. This isn't randomness, it's the cosmic web, the grand architectural blueprint of the universe, and the master builder behind it all. Dark matter's invisible scaffolding, shaping everything from the tiniest galaxy clusters to the largest voids where almost nothing exists. The story begins just after the Big Bang, when minuscule quantum fluctuations, ripples in the newborn universe, served as cosmic seeds. Over eons, dark matter's gravity amplified those tiny wrinkles, pulling matter into dense knots and filaments while leaving vast, empty regions between them. Picture pouring syrup onto a pancake and watching it form branching rivulets, except here, the syrup is galaxies and the pancake is the fabric of spacetime itself. Projects like the Sloan Digital Sky Survey have painstakingly charted this structure, revealing a web so vast it defies human scale. Yet for all its majesty, the cosmic web holds puzzles. Supercomputer simulations, based on our best understanding of dark matter, predict a universe with slightly more tangled filaments and fewer gaping voids than we actually observe. It's as if nature left out a few stitches in the grand design. Some researchers suggest this mismatch could hint at exotic dark matter properties, maybe particles that interact weakly with each other, smoothing out the web's texture. Others wonder if dark energy's accelerating push plays a role, stretching voids wider over time. The implications go far beyond aesthetics. The web's structure encodes secrets about dark matter's nature, the universe's expansion rate, even the mass of elusive neutrinos. Upcoming telescopes like the ESA's Euclid will map millions more galaxies, probing the web's finer threads with unprecedented clarity. Each new data point is a clue, helping us unravel why the universe built itself this way and what invisible forces are still shaping it today. Stand back, and the cosmic web is more than a pretty pattern. It's a fossil record of dark matter's influence, a roadmap to the universe's past, and a puzzle waiting to be solved. And the closer we look, the clearer it becomes. The real marvel isn't the galaxies we see. It's the hidden hand that arranged them. The story of dark matter's discovery starts not in the void of space, but in the careful observations of one groundbreaking astronomer. Vera Rubin spent nights peering through telescopes, tracking the motion of stars swirling around distant galaxies, and what she found shattered expectations. The outer stars weren't lagging behind as physics predicted. They were racing just as fast as those near the galactic core, as if gripped by some unseen hand. This wasn't just a small anomaly. According to Newton's laws, stars farther from a galaxy's center should orbit more slowly, like planets in our solar system, Saturn ambling compared to Mercury's sprint. Yet Rubin's data showed flat rotation curves, a straight line where there should have been a steep drop-off. The only explanation, an enormous halo of invisible matter, its gravity tugging on those outer stars, keeping them from flying away. That revelation in the 1970s became dark matter's first solid evidence, transforming cosmology forever. But the plot thickens. Not all galaxies follow Rubin's rule. Some ultra-diffuse galaxies spin bafflingly slow, as if they're missing dark matter altogether. Others, like the ancient Dragonfly 44 galaxy, rotate so fast they disintegrate without an absurd amount of hidden mass, far more than standard models predict. These outliers force astronomers to ask, is dark matter's distribution more complex than we thought? Could interactions between dark and ordinary matter vary in ways we haven't accounted for? The hunt for answers has led to sharper tools and clever workarounds. Radio telescopes now trace the motion of hydrogen gas far beyond a galaxy's visible edge, mapping the true reach of its gravitational influence. Meanwhile, simulations test whether galactic collisions might strip away dark matter in some cases or concentrate it in others. Every new observation chips away at the mystery, revealing a universe where the rules aren't just hidden, they're still being written. What makes rotation curves so powerful is their simplicity. They don't require exotic detectors or billion-dollar colliders, just starlight and the patience to measure its dance. Yet decades after Rubin's discovery, they continue to challenge and surprise us, because in the end, galaxies aren't just collections of stars. They're cosmic scales weighing the invisible against the known and tipping the balance toward something far stranger than we ever imagined. Here's your script segment, crafted to flow naturally from the previous content while exploring dark matter halos with fresh perspective and depth. If galaxies were cities, their dark matter halos would be the sprawling suburbs, unseen but vital, shaping everything from traffic patterns to future growth. These gigantic, invisible cocoons stretch up to 10 times farther than a galaxy's glittering disk of stars, their gravitational pull acting as cosmic glue. Without these halos, galaxies would fly apart like spinning tops losing their balance. But what's truly bizarre, the way these halos fail to match our best predictions. For decades, supercomputer simulations painted a clear picture. Dark matter halos should be densest at their cores, with sharp cusps of concentrated mass near the center. Yet telescope observations tell a different story. Many galaxies, like our Milky Way, appear wrapped in halos with smoother, flatter cores, more like a softly blended gradient than a sharp peak. This mismatch, dubbed the core vs cusp problem, has become one of dark matter's most nagging puzzles. One leading theory suggests that ordinary matter, stars, gas, and supernova might stir up the dark matter like a spoon swirling cream into coffee. When young galaxies blazed with violent star formation, their explosive energy could have pushed dark matter outward, smoothing the central cusp into a gentler core. Others propose a wilder idea. Maybe dark matter particles aren't entirely dark. If they occasionally bump into each other, even faintly, those interactions could redistribute mass over cosmic time. The stakes are higher than they seem. If halos are fluffier than simulations predict, it could mean dark matter behaves in ways our models don't account for, perhaps with hidden forces or quantum quirks. Alternatively, the flaw might lie in how we model ordinary matter's influence, meaning galaxies are even more dynamic than we realized. New tools are sharpening the debate. The Gaia spacecraft maps the Milky Way's halo with unprecedented precision, while upcoming telescopes like the Nancy Grace Roman will probe halos around distant galaxies. Every data point adds clarity or complexity to the mystery. One thing's certain, dark matter halos aren't just passive wrappers. They're active players in galactic evolution, and their secrets could rewrite the rules of the cosmos. This segment balances scientific rigor with vivid analogies, acknowledging competing theories while maintaining momentum. The tone remains inviting yet authoritative, and the core cusp debate is framed as a thrilling detective story rather than a dry discrepancy. Let me know if you'd like any refinements. Cosmic theory promised us a bustling metropolis of dwarf galaxies swarming around the Milky Way, thousands of them, according to supercomputer simulations. Yet when astronomers sweep the skies, they catch only a few dozen. Where are the missing mini-galaxies? This discrepancy, known as the missing satellites problem, isn't just a head-scratcher. It's a full-blown crisis for our understanding of dark matter's role in the universe's smallest structures. Zoom in on these elusive dwarfs and the plot thickens. Some, like the infamous Dragonfly 44, defy logic. A galaxy so faint it's barely visible, yet its stars whip around at speeds that demand a staggering 99% dark matter to hold it together. That's not just unusual, it's like finding a featherweight boxer who punches harder than a gorilla. How can galaxies with virtually no visible mass pack such gravitational muscle? One camp argues the missing dwarfs aren't gone, they're just too dim for current telescopes to spot. Picture trying to count fireflies from a speeding car, only the brightest catch your eye. Upcoming observatories like the Vera Rubin telescope might soon reveal this hidden population, flooding the cosmic census with faint, ghostly galaxies. But another possibility is far more radical. Dark matter might not clump the way we thought. Simulations assume it's cold, slow-moving, and prone to forming dense, small-scale structures. If dark matter particles are instead slightly warmer or more dynamic, they could resist clustering into tiny halos, leaving fewer dwarfs than predicted. It's the difference between flour settling into fine grains versus coarse crumbs. The stakes: this isn't just about tallying galaxies. If dwarf formations don't match predictions, it could mean dark matter's properties, its temperature, interactions, or even its fundamental nature are wildly different from textbook models. Each oddball like Dragonfly 44 is a clue pushing astronomers to ask, are we missing galaxies, or is the universe hiding a darker, stranger truth? Either way, the hunt for these cosmic runts is more than a cleanup exercise. It's a stress test for cosmology itself, probing whether our theories hold up where the universe gets weirdest. And if history's any guide, the smallest galaxies might just force the biggest revisions. At first glance, the universe seems to keep excellent accounting records, except when it comes to its own ingredients. Scientists know roughly how much normal matter, or baryons, should exist based on the early universe's chemical recipe. Stars, planets, and galaxies only add up to about half that number. So where's the rest? The answer isn't in some exotic dark particle, it's hiding in plain sight, woven into the very fabric of space itself. Enter the warm, hot intergalactic medium WIMP, a ghostly network of gas filaments stretching between galaxies. Picture steam rising from a hot cup of coffee, barely visible yet carrying real substance. This diffuse plasma is scorching up to 1,000,000 degrees, but so thin, it's practically transparent. That's why even our best telescopes struggle to spot it. Yet when they do, the detections are breathtaking. The Chandra X-ray Observatory has glimpsed faint wisps of oxygen ions glowing in this intergalactic fog, like finding footprints in cosmic dust. But finding the WIMP isn't just about completing a ledger. These filaments are cosmic highways, funneling matter into galaxies and sculpting the large-scale structure of the universe. Simulations suggest they could hold 30 to 50% of all missing baryons, with the rest possibly tucked into even more elusive forms, perhaps as rogue hydrogen atoms drifting through voids. The hunt is pushing technology to its limits. Astronomers now use distant quasars as backlights, analyzing how their light dims as it passes through these invisible gas clouds. Other teams chase the WIMP faint X-ray glow, while upcoming missions like ESA's Athena will map it in unprecedented detail. Here's the twist: solving the missing baryon mystery doesn't just balance the books. It reveals how the universe recycles matter, building galaxies from intergalactic vapors. Even the ordinary stuff, it turns out, has extraordinary tricks for staying hidden, proving that in the cosmos, the simplest questions often lead to the most astonishing answers. Some of the universe's most mysterious messages arrive without warning, blasts of radio energy so powerful, they outshine entire galaxies for a fraction of a second. Fast radio bursts, or FRB, are like cosmic Morse code, flashing across billions of light years before vanishing as quickly as they appeared. First discovered in 2007, these millisecond pulses have astronomers scrambling for answers. What could possibly generate such intense, fleeting energy? The plot thickens when we follow the breadcrumbs these bursts leave behind. As FRBs race through space, they pass through clouds of electrons, invisible particles scattered between galaxies. These electrons bend and delay the radio waves, leaving fingerprints in the signal. By decoding those distortions, scientists have uncovered something astonishing. FRBs might be lighting up the universe's missing matter. Remember those baryons hiding in the warm, hot intergalactic medium? These bursts could finally help map that elusive cosmic fog, turning each FRB into a flashlight illuminating the dark corridors of space. Yet for all their utility, the origins of these bursts remain wildly controversial. Some seem to come from highly magnetized neutron stars, their crusts cracking under intense pressure like celestial earthquakes. Others repeat at random intervals, defying predictions, including one infamous signal from a distant dwarf galaxy that flickered like a faulty street lamp. Could these be natural phenomena, or is there a slim chance we're glimpsing something far more speculative? The sheer variety of FRBs deepens the intrigue. A handful arrive with a telltale scream of polarized radio waves, suggesting they've traveled through violent magnetic fields near black holes. Others are eerily clean, as if their journey was undisturbed. Each new detection adds another piece to the puzzle, pushing telescopes like CHIME in Canada and ASCAP in Australia to scan wider swaths of sky, hunting for patterns in the chaos. What makes FRBs so thrilling isn't just their mystery, it's their potential. These fleeting signals could revolutionize how we weigh the universe, probe the structure of cosmic voids, or even test Einstein's theory of relativity. And if we ever pin down their source, it might reveal a new class of celestial objects we never knew existed. For now, every burst is a reminder. The cosmos is still full of surprises, broadcasting secrets in a language we're just beginning to understand. Imagine particles so elusive they can pass through a light year of solid lead without a single collision. Neutrinos, nature's ultimate ghostly travelers, are doing exactly that right now, streaming through your body by the billions. For decades, physicists assumed these subatomic phantoms were weightless, zipping through the cosmos at light speed. But in a stunning twist, experiments deep underground revealed something revolutionary. Neutrinos have mass. Not much a fraction of an electron's already tiny heft, but enough to shake our understanding of the universe's building blocks. This discovery came from watching neutrinos pull a cosmic disappearing act. As they race through space, these particles spontaneously morph between three different flavors: electron, muon, and tau neutrinos. This bizarre behavior, called oscillation, only makes sense if neutrinos have some mass, however minuscule. Detectors like Japan's Super Kamioka, a giant tank buried under a mountain, have captured this metamorphosis in action, neutrinos changing identities like undercover agents mid-mission. But here's where dark matter enters the picture. While neutrinos are abundant enough to collectively outweigh all visible stars, their restlessness rules them out as the primary culprit behind dark matter's gravitational grip. Their tiny mass comes with a catch. They move too fast, earning the label hot dark matter. In the cosmic tug of war between gravity and motion, speedy neutrinos resist clumping into the dense structures like galaxy halos that dark matter seems to sculpt. Yet their role isn't just a footnote. Neutrinos may be the universe's background static, subtly influencing how galaxies cluster on the largest scales. Simulations show that if dark matter were purely cold, cosmic structures would look even lumpier than we observe. Neutrinos' light, fast nature might be the missing ingredient that smooths out the recipe, like a sieve sifting flour to remove clumps. What's truly mind-bending is the scale of their silence. Each second, trillions of neutrinos from the Sun alone pierce Earth unnoticed, a silent storm we've only just learned to measure. Their existence hints at physics beyond the standard model, possibly tied to undiscovered particles or extra dimensions. And while they may not solve dark matter's biggest puzzles, neutrinos remind us, sometimes the universe's smallest players hold the keys to its grandest mysteries. Even the emptiest corners of the universe are anything but still. According to quantum physics, what we call nothingness is actually a turbulent sea of activity, virtual particles flickering in and out of existence so fast they tease the very fabric of reality. These fleeting disturbances, known as quantum fluctuations, aren't just theoretical oddities. They carry real energy enough, in theory, to power entire universes. Yet when cosmologists try to connect this quantum vacuum energy to dark energy's observed effects, the numbers spiral into absurdity. The math predicts a value 1 followed by 120 zeros times stronger than what we actually measure, a miscalculation so vast it's been called the most embarrassing discrepancy in all of physics. So where does this staggering error come from? Picture trying to weigh a single snowflake, but your scale can only register the mass of an iceberg. Quantum field theory calculates vacuum energy by summing up every possible particle fluctuation across infinite frequencies, a bit like adding the vibrations of every instrument in an endless orchestra. The result should be deafening, yet observations of dark energy's gentle push on cosmic expansion suggest the real effect is barely a whisper. Some theorists argue there must be an undiscovered cancellation mechanism, a cosmic symmetry that neatly zeroes out most of this energy behind the scenes. Others wonder if we're fundamentally misapplying quantum rules to gravity's domain. The stakes couldn't be higher. If vacuum energy truly matched theoretical predictions, galaxies would have torn apart before stars even formed. The fact that we exist at all hints at either an incredibly precise balancing act or a gaping hole in our understanding. String theory offers one possible fix, suggesting extra dimensions might soak up excess energy like a sponge. Alternative approaches propose dark energy isn't constant but evolves dynamically. Its current value just a fleeting phase in a much longer cosmic cycle. Despite the confusion, this paradox isn't just a dead end. It's a beacon pointing toward deeper truths. Future experiments measuring the universe's expansion with even finer precision could reveal whether dark energy changes over time, offering clues to this cosmic accounting error. Meanwhile, particle physicists hunt for signs of supersymmetry, a theoretical framework that might help balance the quantum books. What makes the vacuum energy puzzle so captivating isn't just the math, it's the philosophical weight. If empty space holds such unimaginable latent power, barely restrained by unknown forces, then reality is far stranger than it appears. The void isn't passive. It's a sleeping giant, and we're just beginning to guess at what might wake it. For a man who reshaped our understanding of space and time, even Einstein wasn't immune to second guesses. In 1917, wrestling with equations that described a static universe, he scribbled a small Greek letter lambda into his field equations. This cosmological constant was a fudge factor, a mathematical counterbalance to gravity that kept the cosmos from collapsing under its own weight. But when Hubble proved the universe was expanding, Einstein famously called lambda his greatest blunder. Irony strikes hard. Decades later, astronomers discovered the universe's expansion wasn't just continuing, it was accelerating, as if something were actively pushing space apart. That something, a force eerily similar to Einstein's discarded constant. Lambda had staged a comeback, rebranded as dark energy's calling card. Yet this resurrection came with a catch. Its measured value is absurdly, inexplicably tiny. Here's why that's mind-bending. Quantum physics suggests empty space should fizz with enough raw energy to rip atoms apart instantly. But lambda's observed effect is 120 orders of magnitude weaker, like expecting a hurricane and feeling only a breath. Even stranger, tweak lambda slightly upward and galaxies never coalesce. Nudge it downward and the universe collapses before stars ignite. This razor-thin margin for life has physicists debating whether we're seeing cosmic accident or evidence of undiscovered principles. Some propose radical fixes. Could lambda be dynamic, decaying slowly from an initial high value? String theory offers another angle. Perhaps countless universes exist, each with random constants, and we simply inhabit the rare one where lambda's value permits complexity. Others argue the answer lies in rethinking gravity itself beyond Einstein's framework. What makes lambda so compelling isn't just its scientific whiplash from blunder to cornerstone, but what it reveals about our place in the cosmos. Whether it points to multiverses, new physics, or sheer luck, one thing's clear: Einstein's mistake might yet hold the keys to the universe's deepest secrets. Picture waking up one cosmic morning to find the universe unraveling at the seams, not in billions of years, but in a sudden, violent finale. This isn't just science fiction. Phantom energy, a hypothetical twist on dark energy, paints a scenario so extreme it makes black holes look tame. Unlike ordinary dark energy, which gently accelerates the universe's expansion, phantom energy would grow stronger over time, its repulsive force spiraling out of control. The result, a cosmic cataclysm called the Big Rip, where every structure from galaxy clusters to the atoms in your body is shredded apart in a final, terrifying instant. The math behind this apocalypse is as elegant as it is unsettling. If dark energy's equation of state, the ratio of its pressure to density, dips just slightly below -1, its push against gravity doesn't just persist, it intensifies. Space stretches faster and faster until even the forces binding atomic nuclei can't keep up. Galaxies would vanish first, ripped away into an ever-darkening void. Stars and planets follow, torn from their orbits. Finally, in the last microseconds, molecules, then atoms, then space-time itself would disintegrate. No black holes, no remnants, just an infinite, featureless void where a universe once thrived. Is there any evidence this nightmare scenario is real? So far, observations of distant supernova and galaxy clustering suggest dark energy behaves like Einstein's cosmological constant, steady and unchanging. But cosmology is a game of error bars, and phantom energy lingers at the fringes of what's possible. Some models even suggest a milder little rip, where expansion accelerates destructively but never quite reaches infinity. What makes phantom energy more than a morbid thought experiment is what it reveals about how little we truly grasp dark energy's nature. Is it truly constant, or could it evolve, or worse, flip into this catastrophic mode? Upcoming projects like the Dark Energy Spectroscopic Instrument, DAISY, will scrutinize dark energy's behavior across cosmic time, hunting for hints of instability. Whether the Big Rip remains fiction or forewarning, its lesson is profound. The universe's fate hinges on forces we've only just begun to measure, and the darkest energy might still have surprises in store. After all, in a cosmos where empty space holds the keys to existence, even the unimaginable deserves a second glance. What if the force driving the universe's expansion isn't set in stone? The Standard Model paints dark energy as a constant, Einstein's lambda, unchanging across space and time. But nagging inconsistencies like the Hubble tension have scientists questioning whether the cosmos might be shifting gears. Enter Quintessence, a radical idea that reimagines dark energy as a dynamic field, ebbing and flowing like an invisible tide. Unlike the rigid cosmological constant, Quintessence behaves more like a cosmic thermostat, its strength potentially varying as the universe ages. Some models suggest it could have been stronger in the past, weaker now, or even oscillating between phases. This flexibility could explain why measurements of today's expansion rate clash with predictions based on the early universe. If dark energy isn't constant, it's like discovering the gas pedal in your car has been subtly pressing itself harder over time, a revelation that would rewrite our cosmic roadmap. The hunt for evidence is already underway. Telescopes like the upcoming Euclid space mission will map billions of galaxies across cosmic history, tracing how dark energy's push has evolved. By studying the distribution of galaxy clusters and the stretching of space at different epochs, astronomers hope to spot telltale signs of quintessence, perhaps a gradual weakening of dark energy's grip or unexpected fluctuations in the expansion rate. Other projects like DAISY, the Dark Energy Spectroscopic Instrument, are analyzing the faint fingerprints left by Baryon acoustic oscillations, frozen ripples from the early universe that serve as cosmic yardsticks. Critics argue that quintessence introduces unnecessary complexity when a simple cosmological constant still fits most data, but its theoretical allure is undeniable. A dynamic dark energy could bridge gaps in our understanding, from the Hubble tension to the universe's ultimate fate. If Lambda can change, the cosmos might be headed not for a slow fade or a big rip, but for a future we haven't even imagined, one where the rules of acceleration are still being written. Whether quintessence is real or just a compelling what if, its exploration proves a vital point. In our quest to decode the dark universe, staying open to surprise isn't just good science, it's the only way forward. After all, if history's taught us anything, it's that the universe loves a good plot twist. Here's your script segment on Chameleon Particles, crafted to maintain the video's momentum while introducing fresh perspectives and clear explanations. Most cosmic mysteries stay stubbornly consistent, except this one. Imagine a form of dark matter so clever, it changes its very nature depending on where it hides. Enter chameleon particles, hypothetical shape-shifters that act like heavyweight anchors inside galaxy clusters but turn nearly massless in the emptiness of space. This isn't science fiction, it's a serious attempt to solve one of dark matter's most frustrating puzzles. If these particles exist, they'd be the ultimate cosmic undercover agents, altering their properties to evade capture. Why would dark matter need such a trick? Think of it like a fugitive adapting to different environments. In crowded places like galaxy clusters, chameleon particles could interact strongly with gravity, explaining the tight grip we observe on visible matter. But here on Earth, or in the sparse voids between galaxies, they might lighten up, barely making their presence known. This could explain why underground detectors, tuned to spot heavy dark matter particles, keep coming up empty. The culprits aren't missing, they're masters of disguise. Hunting them requires equal parts ingenuity and patience. Scientists are designing experiments that exploit the one place chameleon particles can't hide, the vacuum. In ultra-sensitive chambers, researchers suspend tiny metal orbs in near-perfect emptiness. The theory, if chameleon particles exist, their mass should spike in this low-density environment, creating a faint but measurable force on the orbs. Other teams are repurposing neutron microscopes or even satellite data, searching for subtle anomalies in how these particles might bend light or warp space differently than expected. Critics argue the idea stretches Occam's razor. Why invent complex physics when simpler dark matter candidates remain plausible? Yet the chameleon theory refuses to fade, partly because it elegantly bridges gaps in our observations. If confirmed, it wouldn't just solve the detection problem. It would reveal a dark sector far more dynamic than we ever imagined, where particles play by rules that change with the cosmic neighborhood. For now, the hunt hinges on delicate, painstaking tests, each one a high-stakes gamble that might finally force these cosmic chameleons into the light. Whether they're real or not, their very possibility reminds us the universe's greatest secrets might not just be hidden, they could be actively hiding. This segment balances scientific depth with vivid storytelling, presenting chameleon particles as both a compelling hypothesis and a narrative hook. The tone remains warm and authoritative, avoiding jargon while maintaining curiosity. Let me know if you'd like any refinements. The universe's shyest particles might finally be breaking their silence. We've always pictured dark matter as the ultimate loner particles that drift through each other without a second glance, like strangers in an endless cosmic subway. But what if, just once in a while, they actually bump shoulders? This idea, known as self-interacting dark matter, suggests these invisible particles might have a hidden social life, and the evidence could be written in the way galaxies misbehave. Take the cores of dwarf galaxies, for instance. Simulations based on classic, antisocial dark matter predict these regions should be densely packed, like a crowd squeezed into a concert venue. Yet real observations show them far more spread out, as if something's pushing particles apart. If dark matter occasionally interacts, even weakly, those collisions could act like an invisible pressure, smoothing out the central cusp into a gentler gradient. Picture a crowded dance floor where every so often, dancers nudge each other just enough to create breathing room. The bullet cluster, that cosmic collision we mentioned earlier, offers another clue. While its dark matter clearly outran the visible gas, proving it doesn't interact like normal matter, there's a tantalizing hint it might have lagged ever so slightly behind its predicted path. Could that tiny delay be the footprint of dark matter particles briefly scattering off each other, like commuters weaving through a busy crosswalk? Detecting these subtle social cues is no small feat. Scientists are scouring galaxy clusters for asymmetries in dark matter's distribution, while others model how self-interactions would alter the cosmic web's delicate filaments. Underground labs, originally built to catch WIMP, are now tuning their experiments to search for slightly more chatty particles that might deflect off one another before vanishing. Critics argue the evidence remains thin. Most observations still fit the traditional lone wolf model. Yet the possibility lingers, challenging us to reconsider dark matter's personality. After all, if these particles do interact, even rarely, it would mean the dark universe isn't just a sea of passive spectators. It's a dynamic arena where hidden forces sculpt galaxies in ways we're only beginning to glimpse. Whether dark matter turns out to be solitary or sociable, one thing's clear. The cosmos refuses to fit neatly into our boxes, and that's what makes the hunt so electrifying. Every anomaly, every deviation, could be the first whisper of a conversation we've been missing for decades. The universe might not have left us a photograph of its birth, but it could have sent a message written in the very fabric of space-time itself. Primordial gravitational waves are the faintest tremors from the Big Bang, ripples that have been stretching and fading across the cosmos for over 13 billion years. Unlike the gravitational waves we detect from colliding black holes today, these are relics from a time before stars, before atoms, even before light could travel freely. They're the closest thing we have to a cosmic baby picture. Detecting these whispers isn't just about nostalgia. Hidden in their patterns might be answers to some of the universe's deepest puzzles. If dark energy was stronger in the past, or if extra dimensions creased the early cosmos like invisible origami, these waves would carry the fingerprints of those phenomena. The challenge, they're unimaginably subtle, like trying to hear a single raindrop in a hurricane. Current observatories like LIGO, designed to catch the crashing waves from black hole mergers, aren't sensitive enough. That's why scientists are turning to the next generation of experiments, like space-based detectors LISA and pulsar timing arrays, which use the heartbeat of dead stars as ultra-precise cosmic microphones. Critics argue that even with advanced tech, the signals might be too buried in noise to ever decipher. But optimists point to an ingenious workaround: the cosmic microwave background. If primordial waves shook the infant universe, they'd have left a faint twist in the polarization of this afterglow, a curl known as B-mode polarization. Telescopes like the Simons Observatory in Chile are scanning for this telltale swirl, a potential smoking gun from the universe's first trillionth of a second. The stakes couldn't be higher. If we ever capture these echoes, they wouldn't just confirm theories, they'd crack open a window to a time when all the forces of nature were one, when the cosmos was smaller than an atom, and when the rules of reality as we know them were still being written. It's the ultimate cold case, and the clues have been traveling toward us since the dawn of time. The cosmic microwave background, our most pristine snapshot of the infant universe, should be the very picture of randomness, a uniform tapestry of temperature fluctuations stretching in every direction. Yet when scientists scrutinized this ancient light, they stumbled upon something unsettling. The largest scale patterns in the CMB aren't scattered randomly across the sky. They're weirdly aligned with our own solar system's plane, as if the universe winked at us with a cosmic inside joke. Astronomers didn't hold back in naming this anomaly the axis of evil. At first glance, it sounds like a statistical hiccup, the universe's version of seeing faces in the clouds. But the odds of such an alignment happening by chance are astronomically low, roughly 1 in 1,000. That's like rolling a die 50 times and getting the same number every single time. Could our telescopes be picking up some local interference? Skeptics point to potential contamination from the Milky Way's dust or even quirks in data processing, yet even after rigorous cleaning, the alignment persists. This anomaly cuts deeper than a measurement glitch. If real, it challenges a bedrock principle of cosmology, the Copernican principle, which states we don't occupy a special place in the universe. The CMB should look roughly the same no matter where or when you observe it, but if its fluctuations sync up with our solar system's orientation, it implies an eerie connection between the largest and smallest scales, as if the universe left a hidden signature just for us. Some theorists venture into daring territory. Could the axis hint at a pre-Big Bang structure lingering in space-time like scars from a parent universe? Others propose our cosmos might be finite, its geometry subtly warping the CMB's patterns. Even wilder ideas suggest exotic physics, like a primordial magnetic field frozen into the fabric of reality. The irony is palpable. The CMB, long hailed as definitive proof of the Big Bang, now taunts us with questions we can't yet answer. Future missions, like the proposed CMB project, aim to map this radiation with unprecedented precision, hunting for flaws in the data, or confirming we've bumped into something far stranger. One thing's certain, in a universe that prizes symmetry, the axis of evil remains a defiant crack in the cosmic facade. And sometimes it's the cracks that let in the light. Among the subtle temperature variations of the cosmic microwave background, that faded glow from the universe's infancy, one anomaly stands out like a frostbite scar on an otherwise smooth canvas. Dubbed the CMB Cold Spot, this mysterious region stretches over 1 billion light-years and registers significantly colder than any standard cosmological model can explain. It's as if someone left a cosmic freezer door ajar in an otherwise evenly heated room. What could cause such a drastic chill in the aftermath of the Big Bang? Theories swing from the mundane to the mind-bending. On the cautious end, some astrophysicists argue it could simply be a vast supervoid, an enormous bubble of relatively empty space where fewer galaxies and less matter mean less gravitational pull, subtly stretching light passing through it and creating a cooler imprint. Yet surveys like those from the Dark Energy Survey struggle to find a void large enough to match the cold spot scale. The numbers just don't add up. Then there's the more radical possibility. Could this be evidence of a collision with another universe? In the speculative realm of multiverse theories, our cosmos might have bumped into a neighboring bubble universe during its early expansion, leaving a gravitational bruise that cooled the CMB in that spot. It sounds like science fiction, but the idea leverages real quantum cosmology math, though skeptics rightly demand more than just an elegant equation to prove such an extraordinary claim. Others wonder if we're looking at a rare statistical fluke, an unlikely but not impossible random fluctuation in the CMB's otherwise smooth randomness. Yet even here, calculations suggest the odds of such an extreme anomaly are less than 2%. That's not quite lottery ticket territory, but it's enough to keep scientists digging for deeper explanations. New instruments like the Simons Observatory and future CMB satellites aim to scrutinize the cold spot with sharper resolution, hunting for hidden patterns or secondary distortions that could tip the scales toward one theory. What makes this cosmic cold case so compelling isn't just the temperature discrepancy, it's the way it prods at our assumptions about the universe's uniformity. The Big Bang's afterglow shouldn't have such obvious blemishes unless something unexpected happened, either during those first moments or in the eons that followed. Whether the answer lies in overlooked voids, exotic physics, or even a parallel universe's shadow, the cold spot serves as a humbling reminder. Even our best cosmic snapshots might still be hiding secrets in plain sight. And sometimes the coldest corners of the sky hold the hottest debates. The early universe wasn't just hot and dense, it was loud. In the chaotic aftermath of the Big Bang, space itself rang like a bell, pulsing with pressure waves that rippled through the searing plasma. These ancient sound waves left behind a cosmic fingerprint, a pattern so precise we can still find it woven into the distribution of galaxies billions of years later. Welcome to the world of Baryon acoustic oscillations, or BAO, the universe's oldest echo and one of our most powerful tools for measuring its expansion. Picture throwing a pebble into a pond. The ripples spread outward, creating rings where water and debris collect at the edges. Now imagine that pond is the entire observable universe and the pebble was the Big Bang's aftermath. Those ripples, frozen in time as the universe cooled, left galaxies clustered at predictable intervals, roughly 500 million light-years apart. This spacing acts as a standard ruler, allowing astronomers to gauge cosmic distances with remarkable precision, much like using a yardstick to measure how fast a balloon inflates. But here's where things get thorny. BAO measurements confirm dark energy's accelerating push on the cosmos, yet they also deepen the Hubble tension, that nagging mismatch between different methods of calculating the expansion rate. When we compare BAO's ruler to other cosmic yardsticks, like supernova or the cosmic microwave background, the numbers don't quite align. It's as if two clocks, both impeccably crafted, insist on telling different times. Could this discrepancy hint at something deeper? Some theorists suspect undiscovered physics might be subtly warping our measurements. Perhaps dark energy isn't constant but evolves over time, tweaking the expansion rate in ways we haven't accounted for. Others wonder if exotic particles or extra dimensions alter how these sound waves propagated in the early universe, leaving a distorted ruler behind. Even the neutrinos' tiny mass, long considered negligible in cosmic calculations, might play a bigger role than we thought. The hunt for answers is driving a new era of sky surveys. Projects like DAISY, the Dark Energy Spectroscopic Instrument, are mapping millions of galaxies to trace BAO patterns with unprecedented detail, while simulations test how unknown forces could tweak their spacing. Every data point is a clue, helping us unravel whether the tension stems from measurement errors, overlooked variables, or a genuine crack in our cosmological framework. What makes BAO so extraordinary isn't just their precision, it's their persistence. These frozen sound waves have traveled across 13 billion years to deliver a message about the universe's birth and growth. And if they're now whispering about inconsistencies in our models, it's a signpost urging us to listen closer. After all, in the cosmic symphony, even the faintest notes can change how we hear everything else. Hidden behind the Milky Way's dust-choked center, an invisible force tugs at our galaxy with relentless gravity. Along with thousands of neighboring galaxies, we're being pulled toward something massive, an unseen behemoth astronomers call the Great Attractor. This cosmic enigma has lurked just out of sight for decades, warping the motion of everything around it while refusing to reveal its true identity. At first glance, the culprit seems obvious: the Norma Cluster, a dense gathering of galaxies roughly 200 million light-years away. But here's the catch: its combined mass falls far short of explaining the staggering gravitational pull we observe. It's as if we've found a pebble at the center of a whirlpool when the current demands a boulder. Could there be something even bigger lurking behind it, hidden by our own galaxy's obscuring dust? The mystery deepens when we map the larger flow. Entire galaxy clusters, including our own local group, stream toward this gravitational epicenter at speeds exceeding 1 million miles per hour. Some researchers suggest the Great Attractor might be just one piece of a far vaster structure, perhaps the heart of the Laniakea supercluster, a cosmic web of galaxies spanning 500 million light-years. Others speculate about exotic possibilities, concentrations of dark matter so dense they bend space in ways we've never seen, or even primordial flaws in space-time left over from the universe's birth. For now, the Milky Way's dusty disk keeps our view frustratingly blurry, like trying to spot a mountain through thick fog. But new tools are cutting through the noise. Infrared telescopes like NASA's Roman Space Telescope will peer past the dust, while radio surveys chart the motions of hidden galaxies with pinpoint precision. Every fresh observation brings us closer to answering the fundamental question: is this just a supercluster we've underestimated, or a signpost pointing to something far stranger? What makes the Great Attractor so compelling isn't just its pull, it's the reminder that even in our cosmic backyard, mysteries still loom large. After all, when an entire armada of galaxies marches blindly toward an unseen horizon, it's a humbling sign that the universe still holds its cards close. And the next reveal could change how we see our place in the grand celestial flow. Astronomers have long known the universe resembles a cosmic web, vast filaments of galaxies threading through sprawling, empty regions. But few expected to find our own galaxy floating in one of these voids, a bubble of startling emptiness now called the KBC Void. Stretching over 2 billion light-years, this underdense region surrounds the Milky Way like a celestial clearing in an otherwise dense forest. What makes it so puzzling isn't just its size, it's the way this void might be skewing our view of the cosmos itself. Measurements of dark energy rely on the assumption that space, on the largest scales, is roughly uniform. Yet if we're perched inside a giant bubble, our telescopes could be reading the universe's expansion through a funhouse mirror. Imagine trying to gauge ocean currents while drifting in a tranquil lagoon. The calm around you wouldn't reflect the open sea's turbulence. Similarly, the KBC Void's weaker gravity might make cosmic acceleration seem stronger than it truly is, amplifying dark energy's apparent influence. Not everyone's convinced. Skeptics argue the void's existence hinges on tricky galactic surveys, where dust and observational limits could distort the true density. Others counter with stark evidence. Galaxies in our neighborhood recede faster than expected, as if pushed outward by the void's lack of gravitational pull. Simulations compound the intrigue. Some suggest such vast underdensities are rare in standard cosmology, hinting either at a statistical fluke or a gap in our models. The stakes reach beyond academic debate. If voids like KBC are more common than predicted, they could mask fundamental errors in our understanding of dark energy or even gravity itself. Upcoming projects like the Vera Rubin Observatory will test this by mapping millions of galaxies, revealing whether we inhabit an oddity or if the cosmos is frothier than we ever imagined. One thing's certain, the KBC Void forces us to question whether we're cosmic outliers or unwitting pioneers. After all, discovering you live in a bubble isn't just humbling, it's a catalyst to look harder at what lies beyond the emptiness. And sometimes the quietest corners of space speak the loudest truths. As we reach the edge of our cosmic map, one truth becomes undeniable: the universe is far stranger than we ever imagined. From ghostly dark matter bending galaxies into shape to dark energy stretching the very fabric of space, these 30 mysteries aren't just gaps in our knowledge, they're doorways to an entirely new physics waiting to be uncovered. Every breakthrough peels back another layer, only to reveal fresh puzzles lurking beneath. Think of it like restoring an ancient painting. Each brushstroke clears more dust away, but the full masterpiece remains just out of view. Will we one day find dark matter particles flickering in a detector's chamber? Could dark energy suddenly reveal itself as something even more extraordinary? The thrill lies in the not knowing, in the humbling realization that reality's rulebook still has blank pages. For now, the dark universe keeps its secrets close. But that's what makes this journey so exhilarating. Whether you're fascinated by galaxies spinning too fast, voids stretching too wide, or particles that might not exist until we look for them, there's a mystery here for every curious mind. So tell us below which cosmic enigma keeps you up at night staring at the stars. And if you've enjoyed this dive into the shadows, hit subscribe, because the next revelation could be just around the corner, ready to turn everything we think we know on its head. The universe isn't done surprising us, and neither are we.